Hi everyone. This is Dr. S. Venkateswarlu, working as a professor of ECE at IARE. Yeah, today topic is nonlinear applications of operational amplifier as a voltage regulator. Here, somewhat agenda. Okay, so introduction: voltage regulator. Voltage regulations, line regulations, load regulations, series regulator, and shunt regulator. After that, we will try to verify that what you call IC voltage regulator and switching regulator. Based on that, we are concentrating that IC version. Features of 723 regulator. So, of the 3-terminal voltage regulators, this is today's agenda. So based on these agendas, under nonlinear applications of operational amplifier as a voltage regulator, where it is used, what are the functionality, what are the circuit diagram in terms of discrete and IC versions. Okay, now coming to this introduction. Yeah, here in this case, batteries are often shown on a schematic diagram as the source of DC voltage, but usually the actual DC voltage across voltage source is a power supply. We know that one. Here, with reference to this, batteries are often as the schematic diagram as the source of DC voltage, but usually the actual DC voltage source is a power supply. How it is DC voltage power supply is a power. Okay, so there are many types of the power supplies. Yeah, nowadays, wherever you go, we require the power. So which power they are using? How many types are there? Powers. There are many types of the power supplies. So most are designed to convert high voltage AC mains. Of course, from this room, this all we are having that at 230 volts. Okay. But here, mostly are they designed to convert high voltage AC mains electricity to a suitable, what you call low voltage supply for electronic circuit and other devices. Because of we have to show that we have to run this a lot of devices. Based on that devices, we require the voltage supply. That voltage supply may be low or high that time. So we have to collect the information, voltage supply for the electronic circuits and other devices. A more reliable method of obtaining the DC power supply is to transform, rectify, filter, and regulate an AC line voltage. So a power supply can be broken down into a series of blocks. What are the series? The series is each of which performs a particular function. Yeah, the function may be what we call in terms of the power supply or other ways. That power supply, we know that all power supply, a group of circuits that convert the standard AC voltage 120 volts 60 hertz power frequency provided by the wall outlet to the constant DC voltage. Coming to the transformer, a device that step up or step down the AC voltage divided by the what you call wall outlet to a desired amplitude to the action of the magnitude field. So this is for identifying the function block diagram or function. Here it is input is, here it is observed that input. Okay, that here it is observed that 120 volts RMS. So that means in terms of this, so it is given to the transformer. Yeah, the transformer. Yeah, it is the transformer output is given to that rectifier. Okay, so up to this, check it. This all waveform. This is the waveform. It is initially we are given to the transformer. Transformer output is we are right to observe here. So it should be up to this level. Should be rectify something. That means here it is positive off cycle or negative off cycle. So by using this all rectifier, it will appear only positive off cycle here. Full. That means this is one cycle, positive off cycle to negative off cycle. But after using this all rectifier, we will expect this output response. But here we require only some noise is reflected here. Yeah, if it is an unwanted particle is there, that time we require the filter. By using the filter, we will expect the output response of the filter is, this is the response. The time we require the DC. But here it is, we require input is AC only. We will expect either DC or AC or AC or DC. The time we require regulator. Okay, regulator or normal regulator or maybe IC regulator. So that means the load will be activated. But especially this, our studio, it is what is the load here? That camera, the tube lights, and other all tube setup and so on. These are the load. Based on the load, directly we are right to observe this all parameters: power supply, current, voltage, and other parameter. So here it is, the power supply, power supply and transformer. This is the transformer. Before that, the power supply, a group of circuit that converts the standard AC voltage, maybe 120 volts or maybe 230 volts. Like this, we have to follow this. A transformer is given to the rectifier, a rectifier to filter, filter to IC regulator, it is given to that load. So for this case, rectifier. Before that, we are verifying the term first transformer, after that rectifier. Transformer is, this transformer basically we are having that it is the device, the transformer is the device that's set up or step down, step up or step down the AC voltage provided by the outlet to the desired amplitude through action of the magnetic field. This is the functionality of this transformer. Yeah, coming to the rectifier. Yeah, in this rectifier, a diode circuit that converts the AC input voltage to a pulsating the DC voltage. Yeah, the pulsating DC voltage is only suitable to be used as a battery charger, but not good enough to be used as a DC power supply. In especially that is specified that areas like using that instrument in a radio or stereo system on computer and so on. So here this is related to the rectifier. So next one is, there are two basic types of the rectifier circuits. One is HWR, that is half wave rectifier. Next one is full wave rectifier. Yeah, in full wave rectifier, they are using center tap at bridge full wave rectifier. So in summary, on a full wave rectifier, signal has less ripple than half wave rectifier. Half wave rectifier signal. That means if you are using the half wave rectifier, the ripples are more. While we are drawing that device, the circuit diagram of half wave rectifier, so ripples are more. Ripples are more than that our desirability. Okay, so but while we are using that, how to avoid this all ripple, you go for further full wave rectifier. In full wave rectifier, using the center tapped or bridge full wave rectifier, a full wave rectifier signal has less ripple than half wave rectifier signal and is thus so better to apply to a filter. Okay, so using this particular filter, here it is available that transfer output is given to the rectifier output is given to the filter. The filter is basically, it is so we will expect that all ripples are high or low. Based on the ripples are high and low, you can observe which one is suitable for our desirability. So like this. So filter, a circuit used to reduce the fluctuation in the rectified output voltage or ripple. This provides a steadier DC voltage. Next, the filter is given to that regulator. Like our contents are regulated, but here we are concentrating only in terms of which regulator. That regulator may be IC regulator. Okay, so for this regulator, a circuit used to produce a constant DC output voltage by reducing that ripple. That is your task. The ripples should be reduced. Ripple to negligible. Sometimes supposed you have to reduce the ripple to a negligible amount. One part of power supply. Okay, the power supply. Okay, from this step, filter, before that filter, and the rectifier to what you call transformer. Transformer here it is assigned that what you call power supply based on this. So what the necessity of this regulator? By using the regulator or IC regulator, this is the circuit used to produce the constant DC output voltage. We require the DC output should be constant voltage by reducing ripple. Okay, so the ripples are somewhat it is reduced. Okay, or it is what you call ripple to negligible amount, one part of the power supply. Okay, so for this case we have to use the regulator G0. By using the G0 diode regulator for low current power supplies, a simple voltage regulator can be made with a resistor and a G0 diode here within the circuit using this resistor or maybe using this G0 diode. Okay, and G0 diode connected in reverse here. Okay, so G0 diodes are rated by their breakdown voltages, like it is followed by that this value Vz and maximum power Pz. So typically they are using this typical value. So this typical value 400 milliwatts, or maybe we can use 1.3 watts. Okay, there is this typical value. Two basic categories of the voltage regulators are line regulation and load regulation. So the purpose of line regulation is to maintain a nearly constant output voltage when the input voltage varies. Okay, say for example, input voltage is around 230 volts or 20 volts. So how we are line regulation is to maintain the nearly constant output voltage when the input voltage varies. Okay, so like this, the purpose of the load regulation is to maintain a nearly constant output voltage when the what you call load varies. So voltage regulators, two basic categories of the voltage regulators are, just now we have seen that line regulation and load regulation. The purpose of the line regulation is to maintain the nearly constant output voltage when the input voltage varies. The purpose of load regulation is to maintain a nearly constant output voltage when the load varies. Okay, next come to the line regulation. A change in input line voltage does not significantly affect the output voltage of a regulator within certain limits. Here it is, we check it, this one V in is voltage regulator. We have V in and V out, and somewhat it is we require that what you call decrease or maybe increase in input voltage. Okay, by using this what you call the meter. Okay, voltage regulator, that voltage regulator, if it is no significant change in output voltage, so that line regulation change in the input line voltage does not significantly affect the output voltage of a regulator within certain limits. So based on that limit, line regulations, a change in the input line voltage does not significantly affect the output voltage within certain limits. Line regulation can be defined as the percentage change in the output voltage for a given change in the input voltage. Okay, like this, line regulation calculated using the formula as line regulation, where delta V output by delta V in into 100. Okay, line regulation can be defined as the percentage change in the output voltage for a given change in the input what you call voltage. Delta means we know that one, a change in line regulation can be calculated using the following the formulas, mathematical analysis. That line regulation is equal to delta into V out by delta V in into and 100%. Line regulation can be calculated using the formula. So here is line regulation is equal to delta V out by V out by V delta V in into 100. Next come to the load regulation. Here the load regulation, a change in the load current due to the varying the load, that is how we are varying the load. Here it is RL, that RL should be, it is the variable, using this all variable. Okay, so the line a change in the load, a change in the load current due to the varying the load resistor RL has practically no effect on the effect on the output voltage of the regulator within the certain limits. Okay, that means here it is V in is voltage regulators, given to that load is increasing. If it is increasing and what you call decreasing, it's go on increasing that load resistor. Load is increasing or decreasing, it is a variable, no? So the time what the IL and the V out we write to calculate. So, but this case is where V in is equal to voltage regulator. So increasing the or decreasing here. Okay. So here it is no change here, but here directly we are right to comparing this load regulation. Load regulation can be defined as the percentage change in the output voltage from no load to full load. Okay. NL to no load, NL to full load, no load to full load. Okay, so with this load regulation is equal to what you call V node what you call VNL, that means no load voltage minus full load voltage by what you call that full load voltage into 100. Okay, but here it is, we have to specify where VL is the no load output voltage, VNL, VFL the full load output voltage. So load regulation we write to calculate by using this formula. Okay, next sometimes the power supply manufacturers specify the equivalent output resistance R out instead of its load regulation, where RFL so equal the smallest rated load resistance when we full load voltage. So like this, using this all the simple circuit diagram where it is the battery VH is equal to VNL. Okay, with the R means the R out, so load RL within this V out output voltage right to calculate from this case. The output voltage is equal to no load voltage into full what you call load resistance by output resistor by full load resistor. Using the simple circuit diagram, usually can calculate that full load voltage, where full load voltage is equal to what you call no load voltage of full load resistor by output resistor minus full load resistor. So usually can calculate that output V out. Okay, so like this usually can measure the parameters. Okay, yeah, next what do you call rearrange the equation, mathematical equation for this. Okay, if it is V and L, okay, V and L no load voltage is equal to, so what do you call the full load voltage of output resistor minus full load resistor by full load resistor. So that load regulation, using this all formula, usually can calculate the load regulation, percentage of load regulation, where output voltage by full load resistor easily can measure by using this all mathematical notation. Like this all some examples are available. Using this all example, usually can try to calculate that. Before that, types of regulators, we have to enter the types of the regulators. So fundamental classes, what you call classes of voltage regulators are linear regulator and switching regulators. So two basic types of the linear regulator are the series regulator and the shunt regulator. So the series regulator is connected in the series with the load, and the shunt regulator is connected in a parallel with the load. So within this here, where it is series regulator, Vin is this one, load, and shunt regulator. So where Vin is given to that RS is given to the shunt regulator. So the load is connected here. So the series regulator is connected in the series with the load, okay, and the shunt regulator is connected to the parallel with the load. Okay, you can identify the series, which one the series and which one the shunt. Okay, so control element in the series with the load between input and output. Output sample circuit senses the change in the output voltage. Okay, error detector. Okay, that error detector compares sample voltage with the reference voltage, cause control element to compensate the order to maintain the constant output voltage. Okay, here it is. So here it is mentioned that input is that series regulator. Input is given to the series regulator. It should be grounded. So right to verify that output voltage. So where Vin, that Vin is connected with the control element. Before that it is the control element is connected with what we call the output. Output is sample circuit. It is given to the error detection. Error detections to reference voltage. Okay. So with this, error detection compares sample voltage with reference voltage, causes control element to the compensate in order to maintain a constant output voltage. So op-amp series regulator. Here, suppose you have to use the op-amp. The input is unregulated voltage. It is connected. The Vin is connected to R3, the reference voltage. It is connected to the non-inverting terminal. Okay, that R3 is connected to the the G0 diode with the ground. The non-inverting terminal is connected to the the R1 and R2. Okay, for the purpose of error detection. The transistor control element is available key 1. Okay, with R1 and R2 sample circuit, easily can calculate, easily can measure that output voltage in terms of regulated voltage. This is related by using the op-amp series regulator. Within this circuit diagram, the resistor R1 and R2 sense the change in the output voltage and provide the feedback voltage. So the error detector compares the feedback voltage within a G0 diode reference voltage. The resulting difference voltage causes the transistor Q1, controls the conduction to compensate the variation of the output voltage. Refer that previous circuit diagram. Within this diagram, you can analyze this interpretation. The output voltage will be maintained at a constant value of so where output voltage is equal to 1 plus R1 by R2 into that VZ. As per the circuit diagram, you can try to calculate to determine that output voltage. Now that transistor series regulator, since the Q1 is an NPN transistor, output voltage is found as the response of the pass transistor to a change in load resistance as follows. The thing is, if load resistance is increases, load voltage also increases. Since the G0 voltage is constant, the increase in the output voltage VB is to decrease here. So where output voltage is causes VB is to be decreased. Where to decrease the VB, base emitter voltage reduces the conduction through the pass transistor, so load current decreases. Yeah, these offset the increase in the load resistance and the relatively constant, and voltage is maintained by using this transistor series regulators. Using the same circuit here, is going to interpret this the GNR voltage is constant. Where VZ, the increase in the output voltage here, we have to increase this output voltage here, so it causes VBE to decrease. The decrease in the VBE reduces the conduction through the pass transistor, so load current decreases. This offset the increases in the load resistance, and a relatively constant load voltage is maintained. with reference to this transistor series regulator. So the time we have to calculate that VB, where VB is equal to VZ minus output voltage. Okay, the transistor Q1 is in series control element. Okay, G0 diode provides the resistance reference voltage. So using this all are these, you can calculate the all values. We'll see after this. Next, coming to this what you call shunt regulator circuit. Yeah, in this the unregulated input voltage provides current to the load. Okay, some of the current is pulled away by the control element. So we know that all of that control element. If the load voltage tries to change due to the change in the load resistance, the sampling circuit provides the feedback signals to the comparator. That means, so the unregulated by input voltage provides the current to the load. How it is, if the load voltage tries to change due to a change in the load resistance, the sampling circuit provides a feedback signal to the comparator. So the resulting difference voltage then provides a control signal to vary the amount of the current shunted away from the load to maintain the regulated output voltage across the load. Okay, here it is. If it is Vin is given to that RS in terms of that RS, you have to calculate that ESH plus IL. So it is given to the control element. Okay, after that, same RS is RL ISH plus IL. So sampling circuit is given to that sampling circuit is fed to the that feedback signal comparator circuit. That comparator circuit, it is connected with the control through the control signal with the control element. So this is all based on reference voltage. Finally, we are to verify that output voltage where V0 is equal to VL. Like that, that load based on that load resistor. Go on, if it is based on this load resistor, you can calculate IL and ISH. Okay, op-amp shunt regulator. If you are using here in place of that operational amplifier with Q1 and diode, what you call G0 diode, so the VN is connected to the R3 is connected to the inverting terminal, non-inverting terminal. That inverting terminal is connected to the R1 and R2. Okay, that output is connected with the vertical base of that Q1. The emitter is connected with the ground. Collector is connected with what you call Vin and RS. So within this output section, that it is connected to the RL load resistor, you can measure that output voltage, where output voltage is equal to VN. Okay, so when the output voltage tries to decrease due to the change in the input voltage or load current. Okay, that means load current or input. Okay, input voltage or load current in terms of this, using this one. Okay, so load current causes by the change in the load resistance. Okay, if it is using this one, right to calculate this IL and based on this RL, okay, caused by the change in the load resistance, the decrease in the sensed by the decrease in the sense by R1 and R2. Okay, so feedback voltage is obtained. Yeah, that feedback voltage is obtained from the voltage divider R1 and R2 is applied to the op-amp. Okay, op-amp non-inverting terminal. Isn't it? Inverting or non-inverting? Yeah, non-inverting terminal input and compared to the G0 voltage to control the drive current to the transistor. Okay, so the current through the resistor RS. Okay, current through the resistor RS. What happens? This does the control to the drop a voltage across RS so that the output voltage is maintained. So how it is to maintain the voltage? The voltage is maintained. The current through the resistor RS is thus controlled to the drop a voltage across RS so that the output voltage is maintained. Okay, the control element is the transistor. Okay, in parallel with the load, while the resistor RS in series with the load, The operation of the transistor shunt regulator is similar to that of transistor in what you call series regulator, except that regulation is achieved by controlling the current through the what you call parallel transistor, like this. Here unregulated power supply Vin, here it is unregulated power supply Vin, positive to negative. Here it is RS is connected to the what you call G0 diode. So here also the rate observe the current flowing here IB. So the IB is that this terminal is connected to the base. Okay, that emitter is connected to the what you call negative power supply. So it is connected to the load resistor. So the operation of the transistor shunt regulator is similar to that of the transistor in series regulator, except that regulation is achieved by controlling the current through the parallel transistor. Okay, the resistor RS here. The resistor RS, you have to concentrate this RS, where RS drops the unregulated voltage depending on the current supplied to the load resistor. Okay, so within this, voltage across the load is set by a G0 diode, and the transistor base emitter voltage. The transistor base emitter voltage, especially this is the base. Base emitter, transistor base emitter voltage. Okay, so within this, if RL decreases, if it is this RL is decreases, the reduced drive current to the base of Q1, okay, base of that Q1, shunting less control, less collector current, less collector current. That means it is observed less current. Okay, so within this, load current IL is large. Where that load current IL, the load current is large, maintain the regulator voltage across the load. So the output voltage to the load is voltage across the load is set by the G0 diode voltage and the transistor base emitter voltage. If the load resistance decreases, the load current will be large at a value of the increase in the load current causes the collector current shunted by the transistor is to be less. So the current through the RS, so the output voltage is equal to VL is equal to VZ plus VBE. So with this here, if the load resistor decreases, the load current will be large at the value of where IL is equal to VL by RL. So the increasing the load current causes the collector current shunted by the transistor is to be less, where IS is equal to Vin minus VL by RS. So finally the current through the RS is equal to where IC is equal to IS minus IL. This is the example. Now coming to the switching regulator. Okay, the switching regulator is a type of regulator circuit. Okay, which its effects transfer of the power to the load is greater than series and the shunt regulator because the transistor is not always conducting. So you know that how it is conducting, how it is not conducting. So that means the switching regulator passes the voltage to the load is pulses, okay, which then filtered to provide a smooth DC voltage. Yeah, the switching regulator is more efficient than the linear series or shunt type. Okay, it will prefer this switching regulator when you compare that load and shunt type regulators. So that is the importance of this switching regulator because of unregulated input voltage Vin, okay, with input voltage range. So in input and output voltage regulator, so it is connect output input voltage regulator. So load current to verify that IL and regulated output voltage V0. So within this load, based on that load delta V0, load regulator and line regulation, how it is changes, how it is observed. Finally, the switching regulator passes voltage to the load in series pulses, which then filter to provide the smooth DC voltage. That's why by using this all concept, the switching regulator is more efficient than the linear series or shunt series type. Okay, this type regulator is ideally so for high current application, since less power is dissipated voltage regulation in a switching regulator so is achieved by the on and of action limiting the amount of the amount of current flow based on the varying the line and load conditions. So with the switch regulation 90% efficiency can be achieved. If it is more than that or below, usually can verify that practically. So it is if it is based on the load. If you are using that, if it is a line series or shunt type series, or maybe what you call switching regulator, which one is the more efficient or not that much. In switching regulator, step down configuration is available. With the step down, output is less than the input configuration. The control element Q1 is what you call pulsed on and of at variable rate based on the load current. The pulsations of are filtered out by the LC filter like this. So using this R1, Vin is connected to the R1. That what you call that collector is connected to this. What you call this? That emitter is connected to this what L and D1 with the condenser. That R1, R2, and R3. That R1, R2 is connected to the inverting terminal of the op amp. Output is connected to the variable pulse with the oscillator. Okay, so finally, if the load is connected, finally we are to calculating that E out. Okay, so step up configuration. Check it that one compared to the previous circuit diagram. This one is you can compare this one. Here it is inverting terminal is connected with what you call the diode, the what you call cathode. Non-inverting terminal is connected with this R3 and R2. Okay, so like this step up configuration, the difference in the plant's placement of this induction rate and the fact that Q1 is shunt configured during the time when Q1 is off, where this transistor is off. Okay, the transistor is off. The VL is adds to the VC, stepping the voltage by the voltage up by some amount. Okay, so voltage inverted configuration. Check this circuit diagram. Here is the inverting. That inverting terminal is connected to the what you call the diode cathode. So non-inverting terminal is connected what you call this R2 and R3, and output is that operational for output is connected to the variable pulse width oscillator. So output voltage is of opposite polarity of the input. This is achieved by VL forward bias, reverse bias diode during the off times produces the current and charging the capacitor for voltage production during the off time. So with the switching regulator, 90% efficiencies can be achieved by using this all configuration. Now coming to the IC regulators. So regulation circuit in integrated circuit form are widely used because of based on this all efficiency and other parameter. Their operation is no different, but they are treated as the single device with associated components. So here these are the generally 3-terminal device that provides the positive or negative output. Some types have variable voltage output typically, so they are using that 7800 series voltage regulator is used for the positive voltages. So these 7900 series are negative voltage regulators. Okay, this voltage regulators when used with the heat sinks can be safely produce the current values of 1 ampere and greater. Because if you want to use any product, if you want to design any product related system and all, okay, the time they require this IC regulator. The capacitor acts as the line filtration. So IC voltage regulators, several types of the both linear, series, and shunt, and so switching regulators are available in integrated circuits form, like a single IC regulators, contains the circuitry for reference source, comparator amplifier, control device, overload protection, and so on. It is in terms of the single IC regulation contains the circuitry for these all features. Reference source or CA, the comparator amplifier, and CD, control device, overload protection, what you call OP. Yeah, generally the linear regulators are three terminal devices that provides either positive or negative, and output voltages can be either fixed or adjustable. Okay, the fixed voltage regulator has an unregulated DC input voltage Vin applied to one input terminal. A regulated output DC voltage V0 from a second terminal, and third terminal is connected to the ground. So now coming to the fixed positive voltage regulator, the series 78XX regulators are the three terminal devices that provides the fixed positive output voltage. So the fixed voltage regulator has an unregulated DC input voltage Vin applied to what you call one input terminal. A regulated output DC voltage V0 from the second terminal, and the third terminal connected to the ground. So fixed positive voltage regulator, the series is there in the same series 78XX regulator are the three terminal device that provide the fixed positive output voltage. Like this here, positive input, here it is also in the positive input, connected to the capacitor. So with IC series 78XX, it is connected to this ground. Output is connected to the positive output, and more that condenser. Okay, so here we are to observe these are three pin. Pin 1 is input, second pin is ground, third pin is what you call output. Okay, so like this, the next coming to the fixed regulators, an unregulated input voltage Vin is filtered by the capacitor C1 and connected to the ICs in terminal. So the IC's out terminal provides an regulated plus or minus 12 volts, which is filtered by the capacitor C2. The third IC terminal is connected to the ground. Okay, like this here, 7812, where here it is Vin, it is with the C1, and in between that input and output, we have to give that what you call 7812 with the ground. Third pin is connected to the ground. First pin is in, third pin is out. Okay, the third IC terminal is connected to the ground. Okay, so fixed voltage regulator, under fixed voltage regulator, next one is fixed negative voltage regulator. The series 79, here there is the 79XX regulators are the three terminal IC regulators that provides the fixed negative output voltage. The series has the same features and characteristics as the series 78XX regulators, except the pin number are different. How it is different here? Negative input, and the condenser is changed. Okay, so now remaining all are the ground is connected. This also changed here. Negative output. Okay, so negative voltage regulator in the 79XX series. Here IC part is always this is the popular ICs 79. Here it is 7905, 79. Here it is if they are in the 7905. Okay, so the output voltage is minus 5. Minimum voltage is minus 7.3. If you have the 7908 minus 8, minimum voltage is minus 10.5, and so on up to 7909, 7912, 7915. That's why they are using the 79XX series. The series they are using this are 05, 06, 08, 09, 012, 7912, 7915, 7918, 7924. That means is the output voltage it is specified here. The output voltage are specified here, that 5 is like this, 6 is like this, and 8 is also like this, and 9 is it is specified output voltage. Here also minus 12 and so on. That 15 here it is 79 XS in place of 18. The output voltage is P. Yeah, if it is 7924 minus 24 and so on. Okay, so fixed voltage regulators, positive voltage regulator in the series 78XX series. Previous one is 79XX, this case 78. Check it here. Previous one is 79 series. Now we are entering the 78XX, that is followed by positive voltage regulators in the 78XX series. In part output voltage, in part 7805, their output voltage is what you call plus 5 volts. Yeah, 7806 plus 6 volt, 7808 plus 8 volts, 7810 plus 10 volts output voltage is 10 volts. 7812 plus 12 volts, 7815 plus 15 volts, 7818 plus 18 volts, the output voltage is 18 volts, 7824 plus 24 volts, and so on. Next, positive voltage regulator in the 78XX series, here like this IC version here. You can observe that a positive voltage regulator in the 78XX series. Okay, so fixed negative, what you call voltage regulator. The series 79XX regulators are the 3-terminal IC regulator that provides the fixed what you call a negative output voltage. So this series has the same features and characteristics as the series 78XX regulators, except the pin number are different. Okay, so here it is, the pin numbers are different. If it is negative, here it is a negative input, here is a negative input, the capacitor is like this and the ground is connected as well, here is same. Okay, fixed voltage regulator, negative voltage regulator in the 79XX series in terms of the IC part with the output voltage. If it is a 79XX in place of the series 7905 minus 5 volts, 7906 minus 6 volts, 7908 minus 8 volts, 7909 minus 10 volts, here it is voltage varies. 7912 minus what do you call 12 volts, 7915 minus 15 volts, 7918 minus 18 volts. Like this, 7924 minus 24 volts. Output voltage is like this. Okay, like this 15 volt is the fixed voltage regulator in terms of adjustable voltage regulator. Now it is previously it is all fixed. Now it is we will adjust that all adjustable voltage regulator based on the solar. So voltage regulators are also available in the circuit configuration that allows to set the output voltage to a desired regulated value. So that means of course our laboratory purpose there is LM series. The LM series 317 is an example of an adjustable voltage regulator, can be operated over the range of the voltage from 1.2 to 37 volts. Like this here in place of this LM 317. The positive voltage here, previously that negative, now it is the positive input. That capacitor C1, the polarities are changed here. Here somewhat it is adjusted with R1 and R2. Okay, it is with the C2. Now output is connected to the C3. Positive output voltage will be appear. Okay, now come to the switch mode power supply. Here we know that one switching regulator in the technique by which the unregulated power supply is effectively. So how it is effectively? It is in terms of the converting to regulated load power supply power through the use of controlled switching devices. So switching voltage regulators are used where it is required to supply a stable output voltage from the varying the input voltage with the minimum power loss even under varying the load conditions. So if it is the loads are increasing or decreasing, how it is the switching mode power supply? Switching regulation is the technique by which the unregulated power supply is effectively converted to regulated load power supply. Load power. So the simple switching regulator consists of the control switch. That means there we are using the transistor, a low pass filter, and a sampling network. So based on this order, here it is using the switch. Here the control switch. Okay, the control switch is in place of this control switch. Suppose you have to use that transistor. So here also you have to use that filter, and R1 is connected to that transistor. We connect to the ground where Vin is applied unregulated power supply. Okay, like this switch mode power supply in the circuit, S is the transistor used as a control switch. It is switched between saturation and the cutoff. During the on mode, the switch is in a saturation mode with a negligible voltage drop across the collector and the emitter terminal of the switch. There is a off mode. The switch is in cutoff mode with a negligible current through the collector and emitter terminal. As per this, by using the transistor, the circuit S is a transistor. On the contrary, the voltage regulating switch in a linear regulator circuit always remain in the active region. Due to this, current is not passed continuously through the transistor, and hence the power dissipation is reduced to minimize. It should be minimum, to reduce the minimum value. The transistor is switched on and off by electronic, so what we call pulse width modulator. The filter circuit smoothness, the output waveform and the sampling network R1 and R2 controls the duty cycle such that the output voltage remains constant. Okay, IC voltage regulator, basically they are using this is the popular basically two kinds of IC voltage regulators, multi-pin type. Example is LM series 723C. Yeah, 3-pin type. Say for example, they are using 78XX or 79XX. Okay, multi-pin regulators are less popular, but they provide what you call the greatest flexibility and produce the highest quality voltage regulation. That's why they are using the IC version, IC voltage regulator. Due to this greatest flexibility and produce the highest quality voltage regulation. Okay, 3-pin type make the regulator circuit design what you call simple. Okay, so LM723 has an equivalent circuit that contains most of the parts of the operation amplifier voltage regulator. Okay, we have seen that all are here. It has then a what you call internal voltage reference, error amplifier, okay, pass transistor, and current limiter all in one IC package. That means how many here it is? So one is the what do you call that operation amplifier, the transistor 1, transistor 2, generator 1 and generator 2. It has an internal voltage reference, error amplifier, pass transistor and current limiter all in one IC package. So high voltage configuration. So like these designing equations we are going to use in this one. Designing the equation here is output voltage is equal to V reference of R1 plus R2 by R2. So this by using this external external pass transistor and current sensing added in the circuit. To make this output voltage variable, replace R1 with a port. Okay, choose the R1 plus R2 is equal to, it is mentioned that typically it's around 10 kilowatts and C is the 100 picofarad. So R sense is equal to 0.7 by maximum current. Okay, where if you want to calculate that R3 value, where R3 is equal to R1 into R2 by R1 plus R2. Yeah, next IC voltage regulator, low voltage configuration. So using this this configuration, using the same process, we are to calculate the output voltage and IL maximum value, I short and R sense under voltage conditions. Using the same circuit diagram, you can calculate the low voltage configuration parameter. So that means there is the IC 723 with external pass transistor and feedback current limiting. Using this, how it is limiting, IL, it is based on this V0 and IL, R sense and I short and a feedback condition V dash, V0 dash, V here it is 0.7 RL of R4 plus R5 by R5 into R sense minus R4 into RL. Okay, so this are all we know, already we have discussed this block diagram, transistor and so on. So block diagram of voltage regulator, already we have seen this. After the filtering regulator, a block is used. It removes all the ripples from the filter and makes it output voltage smooth. It also keeps the output voltage. Okay, within this what you call constant irrespective of the change in the input DC, what you call DC voltage. It keeps the output voltage constant under variable, okay, variable load condition as well. Okay, yeah, this load regulation is the V node minus V full load. You can follow this all are, okay. Yeah, here it is components of voltage regulator. This is the feedback circuit and stable reference voltage, and what you call pass element control circuit. The feedback circuit helps in the sensing the variation in the output DC voltage. Okay, depending on the feedback and reference voltages, so a control the signal is then produced to drive the pass element to compensate these variations. So, example, pass element, PN junction diode, or BJT transistor, or maybe you can use MOSFET, metal oxide field effect transistor. These all are we have seen different types of voltage regulator. Already we have seen. Suppose you have to recollect this one. Voltage regulators can be implemented using discrete components in circuit, or there is a possibility is IC version. Irrespective of the implementation, voltage regulators can be classified into two types. Already we have seen the linear voltage regulator and the switching regulator. This all also we have seen. Linear voltage regulator when the transistor operates in cutoff state and the saturation state. Okay, so it switches between the off state and the saturation state. Okay, then the regulator is called as switching voltage regulator. Already we have verified this all are. Okay, within this IC, yeah, most popular general purpose precision voltage is IC723. It is a monolithic linear integrated circuit, different physical packages. The package is pin number 1 is current source, inverting input, third pin is non-inverting input, and fourth pin is V reference, fifth pin is VCC, sixth pin is output, VC is seventh pin, and eighth pin is VCC plus, ninth pin is frequency component, and 10th pin is current limit. Okay, so it works as the voltage regulator at output voltage ranging from 2 to 37 volts at current up to 150 milliamperes. It can be used at a load current greater than 150 milliampere. Use of suitable NPN or PNPN transistor for the external pass transistor. Input and output short circuit protection is provided. It has good line and load regulation. We will export 0.0803 percentage. Wide variety of applications of series, shunt, switching, and floating regulator. Low temperature drift and high ripple, what you call rejection, while you are using this IC723 voltage regulators. So low standby current driven drain, and small size, low cost, and relatively easy with which power supply can be designed. Okay, it provides the choice of what you call supply voltage. A three-terminal voltage regulator have the three-terminal, namely input which is unregulated Vn. It is regulated output is V0 and common or ground terminal. These regulators do not require any feedback connections. Yeah, this is the what you call that features while you are operating, while you are using three-terminal voltage regulators. So, three-terminal fixed voltage regulator ICs, there are basically two types of three-terminal voltage regulator fixed voltage IC are available. One is positive output voltage and other has negative. So, output voltage, but the output voltage is fixed. Okay, so now they are using that all 78XS we have seen. This is the positive regulator. The first two digits, that is 78, indicates that the output voltage is positive. Here it is. It is specified the 78. Why it is specified the 78? This is the positive regulator. The first two digits, that 78, indicates that the output voltage is positive. The second two digits, XX, 780001 and so on, XX indicates the output voltage of the regulator. Already we have seen some examples. The available IC of the series 7805 plus volts, 7812 plus 12 volts, 7815 plus 15 volts. The output voltages are shown. In the case, it is like this. To verify this one. Okay. Next, 79XX is also we have seen. This is the negative voltage regulator. The first two digits are 79 indicates the output voltage is negative. So easily can distinguish that one 78XX. What do you call 79XX? It is specified these two digits 78 and 79. Okay, the second two digits XS indicates the output voltage of the regulator. The available ICs of the series are 7905, 7912, 7915. So the output voltages are shown in the brackets like minus 5 volts, minus 12 volts, minus 15 volts, and so on. Okay, this is the 723 voltage regulator IC. If you know that basic regulator power supply voltage regulator and the IC voltage regulator, let us take the look at one of the most popular IC regulator, 723 voltage regulator IC. Yeah, the function block diagram of voltage regulator is, you know that one. It consists of voltage reference source pin number 6 and an error amplifier with its inverting input on pin number 4 and non-inverting pin on pin 5. The series pass transistor pins 10 and 11 and the current limiting transistor on pin number 2 and pin number 3. Yeah, the device can be set to work on both positive and negative voltage regulator with output voltage ranging from 2 volts to 37 volts and output current levels up to 150 milliampere. The maximum supply voltage is 40 volts and the line and load resistance are each specified as 0.01%. Like this is the function block diagram of voltage regulator IC 723 voltage regulator circuit. Here is the pin number 2, limit current 3 and 4. Okay, that V reference is connected to reference voltage VZ and so on. Okay, we have we have seen this all pin numbers. Okay, it is specified each and every pin. Now it is connected. Okay, positive voltage regulator using IC 723. Okay, within this, if it is not a so high amplitude output ripple is possible to occur. That is our task only. Target output ripple is possible to occur. If it is not so high amplitude output ripple is possible to occur. Okay, so these are the 3 terminal voltage regulators. Advantages of regulator. It is very easy to use. It is greatly simplifies the power supply design. IC regulators are small in size, thus overall size of the power supply can be reduced. Cost is very less. IC regulators are versatile. IC regulators are positive with features like built-in protection, programmable output current or voltage, boosting internal short circuit current, limiting, etc. Okay, this is up to this level. So we are to verify that the summary. Here, voltage regulator keep a constant DC output despite input voltage or load changes. Okay, the two basic categories of the voltage regulators are linear and what you call switching. So the two types of the linear voltage regulators are series and shunt. Already is verified. Okay, so the 3 types of switching: step up and step down and inverting, like this. Okay.
Like, share and subscribe. Hit the bell icon for more updates.